All right. So a few definitions I do want to talk about is, I think before polar versus nonpolar. All right. So this is a quick recap. If you are fat, right? If you actually have a, if you're fat soluble, in other words, if you hear the term lipids, nonpolar, right, uncharged, they're all in the same bucket, right? They enjoy being with other lipids, fats, nonpolar, uncharged oils, right? Cholesterol, right? There's one category, they love being together, right? And then there's another category I want to talk about, right? Water, polar, charged, right? Oh, here we go. Hydrophilic, which means I have to call this hydrophobic. Right, so this is the dichotomy I want you to get really familiar with. Water, polar, charged, hydrophilic. Okay, I think that's about it. Now, likes always, I'll just use a different color just so it's neutral. Likes always enjoy being with other likes. This sounds kind of confusing. Okay. In other words, if you are a water molecule, here's a little water molecule, right? And there's another water molecule right here. Naturally, by chance, you will gravitate towards each other. Right? And eventually, you will become a larger water molecule. And let's say I have a really, really large, here's an example. Let's say I have a large container of H2O right over here. If I were to put a drop, let's use yellow for lipids. If I were to put a drop of fat right over here, and another drop of fat right over here, notice these two droplets of fat will not congregate with the water. It'll try to be as far away from the water as possible. But at some point, if these two bump into each other by chance, it will clump together, right? And if we think about it, let's go to our example of our stomach right over here. Here's our stomach. Right, let me just write stomach. And let's say there's aspirin right over here. Right, aspirin is going to be lipid soluble. In other words, it is nonpolar, it is hydrophobic, it is uncharged. They all mean essentially the same thing. All right, they're in the same bucket. So what's going to happen here is that the reason aspirin can go through the stomach in its lipid-soluble form is because if you zoom in, remember, if we look at a stomach cell, I'm going to zoom in right over here, and I'm going to zoom into this part over here. Remember the structure of a cell membrane, all right? That's part of the stomach cell. right? This is let's say this is one stomach cell right over here. I'm not going to draw the whole thing out, right? And this here is aspirin. Notice the only way aspirin, I don't want to say the only, but one of the easiest way for aspirin to go through these stomach cells, right, is if aspirin is in a lipid soluble form. Because what is the majority of this cell membrane? The majority of it is right over here, which is the fatty tail. So the majority of the cell membrane is fat. So if aspirin is also lipid soluble, it can easily cross the stomach cell. And if it can easily cross the stomach cell, notice behind the stomach cell, there's a lot of blood vessels right here, right? And you're probably thinking, if aspirin were to come into the stomach cell, and eventually, let's say aspirin makes its way into the bloodstream, won't aspirin clump together because it's a lipid, right? And the bloodstream has mostly water? Not exactly, because if you notice it, the bloodstream is not really acidic. Remember our formula from Le Chatelier's principle? This is the aspirin form, right, that goes into the bloodstream. Right. But remember, inside the bloodstream, it is not acidic at all. So we're going to have, if you have a decreased amount of protons in the bloodstream, this aspirin will shift to the right and be in its dissociated form and go right through the bloodstream. Right, so isn't that really nice how we can make use of Le Chatelier's principle, acid and bases, and also how medication is absorbed into our bloodstream? So the next video, I'm going to go into Le Chatelier's principle.